Thanks, Randy, and thanks for having me out to talk about some of the really cool animals. So dinosaurs, now we're finally seeing some of the animals that everybody's interested in looking at here. We all know these as these great big unique things that lived in the Mesozoic. Really big sauropods, large tyrannosaurs, carnivorous, meat-eating terrors running around. We have ceratopsians with these great big horns and different ornamentations on their heads, all the way to different shapes like ankylosaurs where they're covered in armor and running around like little tanks, or big tanks, great big tanks. So all of these diverse shapes and sizes and different forms that we have are really characteristic of the dinosaurs that live in the Mesozoic. But these guys mostly live at the end of the Mesozoic, or in the Cretaceous period. So we'll revisit back to this time scale that we saw a little bit earlier with Ken. And the Cretaceous here, we're going at the very youngest, about 65 million years ago. But all those dinosaurs are related to each other and back into time, evolving through the Mesozoic, starting in the Triassic period. And this is where I do most of my research, is in the Triassic period. So as we've already heard really nicely from Ken and then from Selena, we've got two big extinctions that are bracketing parts of the Mesozoic that I care about here. There's the end-Permian extinction, which we can think of as kind of a giant reset button. So going from Ken's preference of having all these mammal relatives running around, being the large predators, the herbivores, everybody basically is on the landscape. That reset button kind of switches everything over. So then we're able to have reptiles coming in. And these fill into those empty niches in terms of the different sizes and shapes and ecological spaces that were left open from those synapsids. So what we know a lot about now is the later part of the Triassic world, the late Triassic. And these are really full of large reptilian animals like you see here. There's some that kind of look like crocodiles are living in the water, some that look like dinosaurs are going after a tasty snack. They're covered in armor. But these aren't actually dinosaurs. These are all relatives of crocodiles and that lived in that part of the Triassic. And a lot of our record now is based on these animals. So most of my research is on those crocodile-looking things in the background, but again, nothing is really what it seems, and those are not crocodiles. So these are called phytosaurs. And a phytosaur, if you were down in the prep lab, you got to see a couple examples of these from really, really nice material from Utah that Randy and his group have collected. These look like crocodiles, but they're not closely related at all. So in our picture here, here's our phytosaur, and then our dinosaurs in the background. And at this time, dinosaurs are kind of little puny guys running around, not the dominant members of the landscape. Phytosaurs really ruled it all. And these would be semi-aquatic predators, big carnivorous teeth, lots of armor down the backs, probably living in those river systems. So we get a lot of preservation of these animals because they're basically living where they get to be preserved. Something that sets them apart that's really easy to tell them from crocodiles is the position of their nose. So they still have these great big long rostra that are full of teeth, but rather than having their external nares, their nostrils down at the end of their snout, they're up a lot closer towards the eyes. And that's just one of the features that sets them apart as their own little group. So we know a lot more about these now from the late Triassic. There's about 35 different species of them. They're all really large. They're distributed all around Pangaea. If we look at kind of an ecosystem snapshot here, which one of these is the croc relative and which is the phytosaur? Again, we're looking at the big guy here as the phytosaur, kind of filling what we would expect for alligators and crocodiles today. And those other little things that are running around kind of trying to avoid being lunch, those are the croc relatives. This is a classic example of what's called convergence, where we get similar shapes evolving through different pathways, different related groups, distantly related groups, ending up kind of looking the same over time. And we see this sort of croc-like morphology appearing at several points through Earth history. So we have our phytosaurs in the Triassic period. We have modern crocodilians kind of assuming this semi-aquatic, elongated snout look sometime in the Jurassic period, a little bit later. And then in the Cretaceous, we have this as well with our actual dinosaurs, with spinosaurids, and of having this great big long face as well. Whether or not they're semi-aquatic is a debate for another day, but potentially. So with all of these groups, we know that they had to have a different kind of starting morphology before they end up at this long snouted look. So whether it's a short snouted carnivorous theropod, a short snouted, very small bodied croc relative like Protosuchus here, but what's going on with the phytosaurs? How do we get to be a phytosaur? Especially when we're starting off with something that's fairly small and just kind of general archosaur relative guy like Euparkeria. So this is a very small animal, short-snouted face, but how do we end up at something that's a lot more intimidating, much bigger? Some of these skulls can be up to 4 feet long in more of the late Triassic phytosaurs, but we have to understand the process of how those morphologies change over time and in what order they did change. So let's step back a little bit and look at the family tree of archosaurs and some of their relatives. And phytosaurs assume a really important part of this tree because they fit in one of 2 places right now. We can think of them as either the cousin of all other archosaurs. So at their living end of the groups, we have crocodilians on one side and then birds on the other as our living representative of dinosaurs today. And phytosaurs are either outside but very close to that total group there, or they fall just inside as the earliest diverging member of that crocodile line within archosaurs. So they have a really important place, not just in terms of understanding the changes that happen within that one group themselves, but for influencing what we think about as happening either within archosaurs as a whole or along that crocodile line branch. There we go. So I've been trying to investigate some of those changes that happen along the phytosaur side of the tree. And one of the specimens that we've been able to look at now with colleagues is this guy from China. So it looks really big as it takes up space on the screen, but the skull is actually super teeny. It's only about this long. And this turns out to be a really important specimen for understanding phytosaur evolution because it's from the middle Triassic. So again, most of what we know for phytosaurs is from the late Triassic. This is really the only specimen we have from that earlier part of the Triassic period. And it tells us some important things about the order of evolution of those morphological features. You get to see my mouse here? No. I will brave using the laser pointer for you all. Maybe not. So if we're looking at the forelimb here, so this guy is really special also because it's articulated. So all of the bones are in the right order. The skull is up here on the upper right, and then you can go through the neck. There's both forelimbs, both arms on there, osteoderms down the back, and all of the ribs there. And then we've got both hind limbs, and then part of the tail. So unfortunately, we don't have the whole thing, but it's really, really great. Very well preserved for what we do have. And we can see a lot of similarities in the arm and in the osteoderms and the rest of the shoulder girdle to what we see in late Triassic phytosaurs. So we know that those features had to change first. But if you look at its head, and let's look a little bit more closely at that, it's much shorter snouted than what we see in any other phytosaur that we know. So that piece of the puzzle came much later. So if we go back to our convergent evolution for the morphology of these guys, we see the phytosaurs did the same kind of thing. They're coming from a short-snouted earlier member of the group. And we kind of knew that already based on the way that their relationships work out. But now we have part of the puzzle filled in a little bit more. So when we see these convergent morphologies appearing, a lot of just so stories can appear about how those morphologies can actually indicate convergence in ecology as well. So just because they look the same, are they all actually doing similar things? Are phytosaurs also eating dinosaurs like our modern alligators are today? Well, we can use a couple of different tools to try and figure this out. So we're not just telling stories, we have some data that go into this too. And one of the things is looking at the faces. So this is not the face of a phytosaur, this is the face of an alligator. And alligators do something really special along with the rest of crocodilians. They have all these little pits. So if you see those circles that are on the outside part of the face there, those are sensory pits and pressure receptors. So when an alligator is swimming through the water, it can actually feel really slight disturbances in that water surface and knows which way to snap its jaws and eat that fish or whatever else happens to be in the way. And we can trace that not just from the external morphology, but to internal anatomy as well. So as part of my Virginia Techness here, we do a lot of CT scanning and applying technology to our fossils. So looking at the inside of the fossils, we're able to get more information than just from the outside. And you can do this with extant animals too. So the study from 2012 here looked at an alligator and traced some of those nerves that go through the face all the way out to those little pits and those domes. And we see evidence from the bones themselves on other animals. So here's a skull of the Spinosaurus there. We see some of those pits at the front of the face. A little bit hard to see there, but there's a few of them. And people have been able to trace the nerve out to some of those pits as well. So do we see a similar thing in our phytosaurs? Let's look at the face of one of them. If you look really carefully, you can see lots of little circles. We're looking at the front of the upper jaw on the top, and then the front of the lower jaw, the same specimen on the bottom there. And lots of little pits all over both surfaces. And when we CT scan these fossils, this is a scan of a different specimen, we can get some sense of the internal anatomy of the fossils that are really nice as well. So in this one, we've got a couple of different things going on. Green and blue are the color of different sinuses that are in the face, so air spaces that are inside there. But the yellow is the important part. So that's one of those cranial nerves that takes all the little branches out to the edge of the face and provides that facial sensitivity. So by this, now we're able to say phytosaurs probably had that same kind of tactile sensation all over the outside of their face, like we see in modern crocodilians and possibly also in that Spinosaur. So it's not just using the anatomical details to get some inferences about the ecology of these animals. We can also look at real evidence of feeding behaviors. And this is pretty rare in the fossil record, but sometimes we're lucky to have it preserved. So this is the slice of a leg bone, not of a phytosaur, but of phytosaur's dinner. So I'm gonna spin this around here and we're gonna make it be see-through. Through the magic of technology, you'll be able to see what's inside of this. Pay attention to that green dot that you see on the outer surface here. I've color-coded different aspects of this bone so you can follow along. So as this guy spins around, we'll be able to see some of the internal anatomy. This is from the upper part of a leg bone of an animal called a rauisuchid. Remember from Salim's talk, we saw Postosuchus. That's part of that group. They're great big terrestrial predators that would look like carnivorous dinosaurs. You can see how that green dot turned into kind of a green triangle in there. That is an embedded tooth in the bone. And we can look not just at the tooth that's stuck in there, but about the tissue that surrounds it. So I can spin that one more time, potentially. Let me go back and do that again, because it's just too cool. Everybody likes that stuff. There we go. All right, so now watch it again as it spins around. All we can see on the external surface of this bone is just a cross-section of the tooth. But using our CT scans, now you can see, well, the whole crown of that tooth is stuck in the bone. So pretty painful event for this poor rauisuchid, but cool information for us. The purple now that's around there and some of the pink are either other bite marks that are on the surface that don't have teeth embedded in them, or healed tissue that's around that tooth. So this gives us two other pieces of information. One is that this leg bone was chewed on twice. One while the animal was alive, one while the animal was not. And around that tooth is healed tissue. So that means that, unfortunately, for this guy, he was chewed on the first time and the tooth stayed in and lived through it. We can put together a little bit of a detective story because we do also do a lot of 3D printing at VT. So that grayish tooth that you see in my hand down there is a model of the actual tooth that's stuck in the bone. So we don't have to destroy the femur or that leg bone to get the tooth out. We can print it and have a copy. And what we're able to say now, again, is that that phytosaur, because that tooth clearly belongs to a phytosaur once we can get it out and actually see it, was attacking that rauisuchid not once, but twice. And rauisuchid lived through it once, not so much the second time. So we have some actual evidence of some of these behaviors. And what's important about this specimen is that we're not just saying now that phytosaurs are top predators in the water, but they can come out of the water and be the top predator on land also, which kind of makes sense. All right. So with phytosaurs, we're getting a better idea of the changes that can happen to have something from this kind of ancestral short-snouted morphology to get to the forms that we're more familiar with in the late Triassic. We have a better understanding of not just the morphologies that have to change, but the ecological changes that have to go along with that as well. But what about everybody else that's living at this time? Do we see any other kinds of changes that are happening with them, or some more evidence of this really interesting convergence? So we can't say phytosaurs are convergent on crocodilians because phytosaurs came first. Do we see other animals in the Triassic that have their morphologies repeated again later on? So for this, as part of my dissertation work, I decided I was going to look at Texas. And this is not just a random choice. This is important because in the 1930s and 1940s, the Works Progress Administration did a bunch of excavations around Big Spring, Texas. And what this did was end up with thousands and thousands of Triassic fossils, late Triassic fossils, from a very small area, being all incorporated into the collection at UT Austin. So this is something that I worked on as part of my dissertation, going through some of this material. And we had the similar players to what we normally see in other late Triassic localities here. Lots of phytosaurs, lots of those armored aedosaurs, some of those big rauisuchids. But something that we were able to find unexpectedly was this dude. So this guy is called Triopticus, and it was collected in 1940, completely unknown, left as a poor little blob of mud in its box until we got to it as part of a class that I was in. And once we cleaned it up, we could see that this little fossil looked a lot more similar to a dinosaur. So it's not a dinosaur, though. We can look at other features of the underneath of the skull, or look at the brain case there, and we see that there are differences. So this is actually more closely related, likely, to the crocodile-line archosaurs. So more of that interesting morphologies that are happening in the late Triassic, but not on the dinosaur side of the tree. And we see a lot of similarities just in the external morphology here. But again, we can apply our CT scanning methods to this and look inside. So a little bit similarity in the brain case, but what was cool about this guy is that that dome, or that thickened area of bone on top of the head, is actually constructed in the same way to what we see in pachycephalosaur dinosaurs from the Cretaceous period. And we found that it wasn't just phytosaurs and Triopticus that are in this late Triassic Texas assemblage. We have other armored quadrupeds, some edentulous bipedal crocodile relatives, some herbivorous animals, all living together. And we see repeated times of all of these morphologies after that Triassic-Jurassic extinction. So something about these morphologies is very important and comes up again in ecosystems over and over. So, and what this allowed us to do was make some predictions about what we would find in the rest of the fossil record. So we did not see out of this group here anything that looks like our giant sauropods, or really anything that looked like ceratopsian dinosaurs. But there's so much other convergence going on that we would say potentially. And luckily for us, the next year, this guy was published. So it worked out really nicely. Shringosaurus looks very similar to our ceratopsian dinosaurs, but it's pretty nice specimen here with lots of parts of the skeleton. And because we have the rest of the animal, we're able to say, no, it's not a dinosaur. It's, again, more closely related to the archosaur group as a whole outside of that one. So this is a case where we have some predicted convergent morphology. Luckily for all of you, we also have some unexpected convergence, which was just published 2 days ago. So we now have this guy, which is just one of the most bizarre Triassic animals ever published at all, ever found. And we had known about basically everything from the neck down for a while now, but no evidence of the head. And this new specimen that was just put out about 2 days ago, we see similarities, not just between other reptiles or these crocodile-line archosaurs in the Triassic and later dinosaurs or later reptiles through the Mesozoic and the Cenozoic, but across to mammals as well. So the skull of this has been compared to the platypus. That's not something you're going to see every day at all. Here's our Triassic guy on the left in this image, and then a platypus skull in the same orientation on the right here. Pretty similar. There you go. All right, so we're able to see that we've got a lot of these different morphologies that are appearing in the Triassic period, either within that crocodile line part of archosaurs, or even in more primitive archosaur relatives that are appearing later on in what we'd always thought were really unique morphologies for dinosaurs or even mammals now, much later in the Mesozoic and the Cenozoic. But these shapes are appearing much, much earlier, and in often times found together in one deposit. And we've heard a lot about now potential reasons why this might be. Ken's talk, I think, set up really nicely that we're looking at these extinctions creating ecological opportunities for diversification and these new shapes to evolve. And because we've got another extinction at the end of the Triassic that wiped out our poor phytosaurs and some of their other late Triassic friends, we're able to see those similar morphologies appearing again in our dinosaurs later in the Mesozoic. So the work that we do can't be done without the help of a lot of graduate students and undergraduate students and interns that help out with us, and of course with lots of funding. So I'm happy to take any questions, and thank you for listening.